Okay, before we proceed with the subject, I want to make an announcement for next week. Next Thursday in the colloquium here, we have a very well-known relativist as a speaker, who, as I expect, will give a very interesting talk on relativity. His name is Reinhard Meinl. He's from the Jena group, which has a big tradition in Germany. So Jena is the relativity center in Germany, was a relativity center for decades. And Reinhard Meinl is one member of this group. So I think it would be a good idea to go to this colloquium talk instead of doing a lecture in parallel and missing this interesting talk. So my suggestion would be that next week we have only one lecture on Friday. And on Thursday, I would strongly encourage you to go to the colloquium. I expect it to be also of interest for people who have not a big background knowledge on relativity already. I'm fairly sure that he will begin with an introduction which is useful also for non-experts. So that's the plan for next week. Now let me continue. And I will send around an email with this information so that everybody knows about this. But I wanted to mention it already now. Okay, what are we doing at the moment? We are talking about covariant derivatives now. We want to learn how to differentiate tensor fields. And the last thing I did yesterday was that I briefly explained, not really worked out, but briefly explained the general idea why the usual partial derivative is not a good way of differentiating tensor fields. And the argument was it doesn't give a tensor field. Of course, we want to have a differentiation which is independent of the chosen chart. So it should give the same geometric object independent of which chart I'm using. And for this, we need an extra structure. And today we will discuss this extra structure in detail. That's what is called a covariant derivative. So I begin with a definition. A covariant derivative on a manifold. Oh, there's also another word, covariant derivative or a linear connection. These are two words for the same thing. Or linear connection on a manifold M. It's a map which is usually denoted by del, sometimes capital D, but it's more common to write del. And it's a map which has two slots, and in either slot I am expected to fill a vector field, and what it gives me back is again a vector field. So I need two vector fields as the arguments, and then gives me back a vector field, and this vector field is usually written in this way, that one writes the x as a subscript and then the y. So the idea is it's supposed to become a differentiation operator, an operator which gives some sort of derivative. So the idea is that the y is the object which is differentiated, and the x gives the direction in which the derivative acts. So that's the reason why one writes it in a non-symmetric way. So the object is absolutely non-symmetric with respect to its two slots. So one is the thing on which the operator acts, and the other thing is this, gives the direction in which the operator acts. And of course, it must have a number of properties with the following properties, so that we can really understand this object as a derivative operator. So as to the first slot, this gives the direction in which the derivative acts. We would expect usual linearity. Yeah, if I know what the operator does in this direction and what it does in this direction, then I want to form linear combination, and the linearity rule should hold. So in the lower entrant, in the lower slot, I just want to have linearity. So if I insert a sum here, then this should be the sum of the two individual derivatives. And if I multiply my x with a function f, then I want to have just this here. But with respect to the other slot, because this is supposed to be a differentiation operator, I will not require linearity with respect to coefficients with their function. I will rather require something like a product rule. A differentiation operator should satisfy a product rule. So I will require a different role with respect to the second slot. So if I insert a sum here, there's no difference. For a sum, I also want to have the distributive law. But the essential thing that if I apply this to a vector field y multiplied with a function, then I do not require that I can take the f out. I rather require a product rule. And the product rule reads like that. This is f del xy plus, and now the term where the x acts on the f. So I apply the x as a derivation to the f, and then I multiply with the vector field y. So these are the two rules. These are the defining properties of a covariant derivative. And I should, of course, write what the objects are, although it's fairly obvious. So this should hold for all. What do I have? x1, x2, y1, y2, x and y are vector fields. And f, I only have one f, right? Yes. F, of course, is a scalar field. So remember, with this curly t, TRS of M, we denoted the tensor fields of rank RS. So the tensor fields of rank 1, 0, these are the vector fields. And the tensor fields of rank 0, 0, these are the scalar fields, the functions. So that's the definition of such an operator. And that's a reasonable thing if we want to interpret this as a derivative. So that's something which is not constructed from structures which are already given on a bare manifold. Yeah, if you have a manifold without additional structure, you cannot construct such an operator out of the things which are given on the manifold. It's an extra structure which has to come from outside. And we call such an extra structure a covariant derivative, or for reasons which will become obvious soon, a linear connection. So there are two remarks. Remember, maps of this sort would be tensor fields if they were linear with respect to coefficients which are function in both entries. Yeah? Then this would be a tensor field. But because of rule B, where we require that we do not have linearity in the second slot, this del is not a tensor field. Yeah, del is not a tensor field. So when we represent it in coordinates, which we will do in a minute, which will give us the famous Christoffel symbols, we will not expect that the Christoffel symbols transform like the components of a tensor. That's already clear from the outset. So the first remark is because of the second property, I wrote Latin 2, because of 2, del is not a tensor field. And the second remark, well, I said it's an extra structure. One has to prescribe such an extra structure if one wants to differentiate tensor fields. The question is, does such an extra structure exist on any manifold? So just for those of you who are interested in mathematical subtleties, I want to mention that one can prove that they do exist. And for this existence proof, again, these topological requirements, A1 and A2, which we usually include in the definition of a manifold, are essential. So if you have a manifold which is not Hausdorff, or which is not second countable, then it might happen that such an object does not exist. But with our definition of a manifold, which includes these two properties, one can prove that covariant derivatives exist on any manifold. And manifold for us always means the infinity manifold with the topological axioms A1 and A2 satisfied. So I write in bracket here A1 and A2 are essential. the proof of existence. Covariant derivative is of course not unique. Yeah? There are many covariant derivatives on a manifold, and we will find out how they are related, how many different covariant derivatives are in the next worksheet. So that's fairly easy. So the answer simply is if I have one, then I get all the other ones by adding a tensor field of the correct rank. So that we will do in the next worksheet. So uniqueness is of course not satisfied. So there's not that's what I said. There's not a naturally given covariant derivative on a manifold. There are many, and it must be given from the outside as an extra structure. Okay. So what this does is it allows us to differentiate tensor fields, and by definition, in a way that the outcome is again a tensor field. Right? Vector fields, in a way that the outcome is again a vector field. Our goal was to introduce a derivative operator on tensor fields of arbitrary rank. So what we have to do now is we have to demonstrate that if we have such a structure, this operator, del x, for any x, can be extended to tensor fields of arbitrary rank. Yeah? At the moment, it's only defined for vector fields. But that's enough. So you have to introduce a structure only on vector fields. And then you can extend it in a natural way, which I explain right now, to tensor fields of arbitrary rank. So given the covariant derivative, the operator del x is well defined. Yeah, where I feed a vector field x in the first slot and leave the second slot open. So then I get a map from T1OM to T1OM. The operator is well defined. Now my claim is that this is already enough to get this operator on tensor fields of arbitrary rank Rs. So we have to extend it to tensor fields of other ranks. So this can be extended to an operator del x, which acts on tensor fields of arbitrary rank Rs. So the object which is differentiated is a tensor field, and the outcome is again a tensor field. That's what we wanted to have, well, what the partial derivatives do not do. Well defined. This can be extended to, for all, Rs by the following rules. So I write down a number of rules, and I claim that then it is clear what this operator does on tensor fields of arbitrary rank. So I know what it does on vector fields. At the moment, I do not know what it does on scalar fields, on covector fields, and then on higher order ranks. So the first condition I write down is that I say what it should do on scalar fields. And on scalar fields, it should do always the same thing, independent of what connection I have. It should always be the ordinary derivative. So I should have del x applied to a function f is just the derivative x applied to the function for all f in 0, 0 of m. So that's the same for all connections. Whatever you choose as a covariant derivative or as a linear connection, the action on scalar fields is always the same. Then I explain what it does on covector fields. So I want to define what is del x applied to a covector field alpha. So this is supposed to be a covector field again. So it's something which eats vector fields. So I have to tell you what it does with the vector field y. And what it does is explained by the ordinary product rule. So I say this is x applied to alpha of y. I know what this is. I could put a bracket here, although it's not absolutely necessary. Yeah? Alpha is a covector field, acts on a vector field, gives a scalar field. So I can apply the x as a derivative to the scalar field. That's well defined. And then, so I have the derivative taken out, and now I bring it in again. So I have a sort of a product rule. alpha del xy. And this is again defined because that's the covariant derivative was explained in these terms. It was explained in terms of acting on vector fields. So this expression is well defined, this expression is well defined, so I know now what it does with a covector field. So this is for alpha in T0, 1, m. So now I have it on scalar fields, vector fields, and covector fields. And now I can extend it to arbitrarily high rank just by telling how it acts on sums and on tensor products. Because any higher rank tensor field can be written as a combination of of sums and tensor products of lower tensor fields. I could think of a basis. Choose a basis for the vector fields, the dx mu's, basis for the covector fields, the dx mu's, and then you can write any tensor field of arbitrarily high rank as a linear combination of tensor products of these basis vector fields. And if I know how the operator acts on tensor products, I then know what it does on the tensor field. So I now say what it does for a sum and what it does for a tensor product of two tensor fields. I denote them A1 and A2. So if I apply nabla x to a sum, in German we usually say nabla. In English one usually says del. By the way, do you know what nabla is? That's quite interesting. Nabla is a Hebrew instrument. It's like a lyra, it's a string instrument, and it has approximately this shape. That's why this operator is called nabla. So this is supposed to be the x1, the xa2 for all a1, a2 of tensor fields of arbitrary rank. So then I can expand linear combinations. And then I need to know what it does with the tensor product. I call the factors A and B. So that's rule number 5. So if I apply this to something of this form, then I want to again have something like a product rule. So I first apply it to the first factor, and then I apply it to the second factor. And the tensor product, remember, makes sense for arbitrary rank. So I can add together two tensor fields only if they have the same rank. Yeah, so both must have the same rank. But I can multiply them in the sense of tensor product for any rank. So here I require that this holds for A from some TRSM, and B may have an arbitrary other rank TR hat S hat M. So, and with these rules, I have defined, it's difficult to count to 4, right? This is 1, 2, I think this is 3. And then this is 4, right? Okay, do I have 4 conditions or did I miss one? No, I think, yeah, that's it. Yeah, and with these rules now, it's clear what the operator does to an arbitrary tensor field. How do I work this out? Well, I write this arbitrary tensor field as a linear combination of my bases, covector fields and vector fields. And then I use these 2 rules. The linearity is evaluated with this rule, and then this tensor product of the basis vectors and basis covectors is evaluated with this rule. And in the end, I end up with the operator only acting on vector fields and covector fields. And this I have explained before what it is. And on scalar fields, the coefficients. Of course, it also acts on the coefficients. So this is now the operator is defined on tensor fields of arbitrary rank. And it has these important properties. It's a linear operator. For each fixed rank Rs, I have this linearity property. And it satisfies a sort of product rule over the tensor product. Yeah? That's a product rule, quite analogous to the standard Leibniz rule, but now in the sense of the tensor product. So these are the rules which satisfy this operator del x. And with the help of such an operator, we can now differentiate tensor fields. Yeah? We can apply this, we can differentiate then in the direction of any vector field we like. Yeah, this lower slot, in this lower slot, we only insert vector fields, nothing else. Yeah? So the second slot was generalized. So here in this slot, we had in the beginning only vector field, and from now on we can insert tensor fields of arbitrary rank. But here we still have only vector fields. This gives the direction in which I differentiate. It doesn't make sense to differentiate in the direction of a higher rank tensor field. Okay, so that's how this operator del x works. Yeah, now we work this out in a chart. And now we will get these expressions which you find for covariant derivatives in the old-fashioned books, which explain everything in terms of charts. And this will bring the famous Christoffel symbols into the game, which are named after a German mathematician, Bruno Christoffel, who actually was teaching at the institute where I studied, or rather at the predecessor institute. I studied at Technical University in Berlin, and the predecessor institute of this university in the 19th century was the institute where Christoffel was working. So in my early students' days, we had a 100-year celebration for Christoffel. Okay, so in local coordinates, such an operator, if we have such a covariant derivative, is characterized by what is called, well, some people call it the connection coefficients. Or more commonly, it is called Christoffel symbols, after the person who introduced it. Too low. What are they? Well, if I want to characterize such an operator in coordinates, I would tell what it does on basis vectors. Yeah? So that's the operator, how it was defined. So it has two slots. I put vector fields into the slots. And when I want to represent it in coordinates, I would put the basis vector field into the slots. And now this is again a vector field, so it can be written as a linear combination of these basis vector fields. And the coefficients which appear here, these are the Christoffel symbols. So they are denoted gamma, tau, mu, sigma. And again, I try not to write indices directly one over the other, although it is quite common. But if you do this, and later you start pulling indices up and down, then you really never know in which position you pull the index if you use this rule of shifting indices. So I try to always leave a gap here. So that's my first index, that's the second, that's the third. That's my convention. Some people who also are careful about index position write the upper one in the third position. So you have to be careful with different conventions. So that's the defining equation of these coefficients. Yeah? Of course, I characterize the operator uniquely in a basis. Yeah, if I know what the operator does with the basis vectors, then I know what it does with arbitrary vector fields, because I can write every vector field as a linear combination of the basis vector fields, and I can use these rules to evaluate this. So this set of coefficients, well, let's count how many are these. If we are on an n-dimensional manifold, then I have n times n coefficients, which determine this, right? So we are mainly interested in 4-dimensional manifolds. When we talk about spacetimes, we have a 4-dimensional manifold. So how many Christoffel symbols do we have? We have 4 times 4 times 4. That's 64, is that true? I think so, yeah. So actually, they will have a particular symmetry. We'll talk about this in a minute, so they are not all independent. But in general, for an arbitrary covariant derivative, they are independent. So we would expect 64 coefficients. So if you write, well, you cannot write as a matrix. You would need a 3-dimensional matrix scheme in order to write this, right? And you would already need quite a lot of entries. So you see again how elegant this index calculus is, where you write this in very compact form. So if you would write out the sum, then it would be an awful long expression. So that's how the Christoffel symbols are defined. And I claim that they satisfy two rules, which is fairly obvious. The first rule is if I apply dx, what letter did I use? I use mu, sigma, and tau, let's say dx rho. If I apply this, d mu, d sigma. So what is this? Well, of course I insert this expression here. So this is dx rho gamma tau mu. It already starts that I write them one under the other. D tau. Now let's see. That's a covector field. It acts on a vector field which is written as a linear combination. Now this is a linear map, so I can take this out. Yeah? So I can write this as gamma tau mu sigma dx rho d tau. And now, what is this here? The rho's covector basis field acting on the tau's vector field. Kronecker, very good. Yeah. So maybe if you don't see it immediately, you can write this. Remember how the operator d was defined. It was defined in the way that this vector field acts on this function. So d tau is d by dx tau, x rho. Yeah? And I think now everybody sees that this is a Kronecker. Delta rho tau. So I can carry out the sum over tau. It just means that I have to replace the index tau by rho, right? So multiplying with the Kronecker and then summing over one of the indices picks out one term of the sum. And it picks out precisely the term which was given by this index. So the result is gamma rho mu sigma. So if you like, you can also define the gammas by this equation. Yeah, you can say, you can view either this equation or this equation as a definition of the gammas. It's equivalent. And the second rule, that's not quite so trivial, but also can also be calculated fairly quickly. Namely, what happens if I apply my derivative operator, say d rho, to the one form, dx tau. Yeah? This operator acts on tensor fields of arbitrary rank. So in particular, I can apply it to a covector field. And that's what I do here. So what is this? How do I write this? You have to use one of these rules. Let me see, which rule do I use? I apply to that's a trick. Yeah. So I apply this. Well, what is this? That's a covector field, right? I have a covector field, and this operator makes covector fields into covector fields. So the whole thing can act on a basis vector d mu. And now I can use the product rule. So I can write this as nabla del rho. Del partial rho. So that's what I meant. dx tau d mu minus dx tau del partial rho d mu. So, well, we have just seen that this here is a Kronecker. So the Kronecker is constant, right? For some pairs of indices it is 1, for some pairs of indices it is 0, but it is always a constant. So the derivative is of course 0. Yeah? So maybe I should introduce an intermediary step just to remind you, this operator acting on a scalar field is just the partial derivative. So this is this rule here. Where is it? This rule. Yeah? If I apply such an operator to a scalar field, then I just get the ordinary, the x acting in the sense of the ordinary derivative on the f. So I can write this expression here as d by dx rho applied to delta tau mu. And now it's obvious that it's 0. Yeah? If I just differentiate something which is constant. And this here is minus dx tau. And now remember how the gammas were introduced. This is gamma mu rho. Oh, I shouldn't use mu. Mu is already in use here. So let's call this mu. So, and the basis vector d tau, d nu. Okay, so that's 0. And here I can take the scalar factor out of the bracket. And I get dx tau d nu, which is the Kronecker delta tau nu. And there's this minus gamma. The nu becomes a tau. Tau rho mu. So that's how the operator acts on the basis 1 forms. Okay, I could write this in a more, in a slightly more complicated way. Let me see, which index do I want to replace? Let me see. Nu sigma. Nu sigma. I want to have rho tau. So I want to replace the mu. Yes, I could write this in a more complicated way. This looks funny at first sight. You will see in a minute why I do this. Yeah, I can write it in this way, of course. Yeah. This looks simpler, so you may ask why writing it in this complicated way. But the idea is that I also get a basis vector d mu here. Namely, this is minus gamma tau rho sigma dx sigma applied to d mu. And now I can compare this one form here to this one form here. Because I have on both sides the thing acting on the basis vector field d mu, and it should give the same expression. So the two one forms must be equal. So I have found what the covariant derivative of a basis covector field is. Namely, it is minus gamma tau rho sigma dx sigma. Yeah, so that's the formula which is analogous to the defining equation. Here we had the thing acting on a basis vector field, and we have written this as a linear combination of this vector field, and we saw this gives us a gammas by definition. Here we apply this to a basis covector field and write this as a linear combination of the covector fields, and what we get as the coefficients are minus the gammas. Yeah? So again we see this. This comes, of course, from the duality, from the product rule. So that for the one forms, we have minus the gammas. So if you like, but that's unusual, you could also start with this equation. You could introduce the gammas by this equation. This would also define them uniquely in a completely equivalent way. Okay, so we know what the covariant derivative does in a chart on the basis vector fields. And then we can calculate what it does on arbitrary vector fields, or covector fields, or tensor fields. So that's what we want to do now. So these were the. So we want to calculate now covariant derivatives of tensor fields of arbitrary rank in terms of local coordinates. This means with the help of these Christoffel symbols in terms of local coordinates. And I will show this in detail for vector fields and for covector fields. And for tensor fields of higher rank, I will just write down the result and hope that you will trust me and that you have, at this stage, you have understood the general procedure. So we begin with vector fields. Begin with a vector field, so that's something of this sort. X mu partial derivative mu, and it's supposed to be a vector field. So, or maybe I should not call it X. Let me see. Yeah, it's okay, I called it X, yeah. I take the derivative with respect to a basis vector field d nu, say. So I want to calculate what is this. The idea is the following. I want to work out this expression, and I want then, that's the vector field again, right? This operator makes vector fields into vector fields. So the whole thing is a vector field. And this vector field can be written as a linear combination of these basis vector fields. And what we get in front of this, the coefficients, that's what we call the local, the representatives in local coordinates of this covariant derivative. And that's what I want to calculate. And it can be expressed, of course, in terms of the gammas. That's the formula I want to derive. So I want to write this as a linear combination of the basis vector fields d by dx mu, and want to see what the coefficients look like. So let's just do this. So this is x mu d mu. And now you see that the gammas enter the stage, right? So this operator satisfies the product rule. Here I have a product of a scalar field and a vector field. So I can use a product rule, which gives me covariant derivative in the direction of partial nu applied to x mu times d mu plus x mu covariant derivative applied to d mu. So the coefficients are just functions. They are scalar valued. So a covariant derivative acting on a function is the same as just the ordinary derivation acting on this function. So this is just d mu x mu d mu. And here, of course, we get the gammas. This can be expressed in terms of the gammas. X mu gamma tau mu mu d tau. So the second term just uses the definition of the gammas. Now I want to combine this in one line, so I want to have the same basis vector here, so I have to rename one of the indices. So I think a good idea is to change the mu into a tau. Of course, I can give any name to summation indices which is not yet used. So I can write it in this way, and then I can write it with a bracket, with the partial derivative outside of the bracket. So I can write it as partial derivative plus x mu gamma tau mu mu d tau. So that's the goal. We have reached the goal which we wanted to reach. We have succeeded in writing this as a linear combination of the basis vector fields. And what we have in front here, the components of the covariant derivatives, that's what one calls the coordinate representation of the covariant derivative. So for this here, one would write, so that's the definition. One would write the covariant derivative. No, it's a nu, sorry. It's a nu, not a nu x tau. So that's the definition. That's a new symbol. That's a del just with an index. That's something we didn't have before. So don't confuse these two symbols here. This is a del with a vector field as a suffix. So this is an operator which acts on tensor fields. This is something which is defined by this expression. And it's an operator which acts on components, not on tensor fields. So don't confuse the two things. The del with an index and the del with a vector field, which may be a basis vector field or some other vector field. So that's what we call the covariant derivative of a vector field in local coordinates. And the people who only think in coordinates, who never write down the invariant objects, they just give this line, this here defined as this here, they give this as a definition of a covariant derivative of a vector field. So they say, the covariant derivative is related to the partial derivative by added this term, which involves the gamma. So that's the definition of this symbol, and they never speak about the general covariant setting where you have this operator del and things like that. They just talk about this object which acts on components. So that's my notation, the notation I will use. When I use index notation, I denote the covariant derivative by del with the index. There are some other notations. So some other authors use other notations. Some other authors they write for partial derivative and covariant derivatives. They use other symbols. And because you find this in many books, I should mention this. One very common rule is that one uses a comma for the partial derivative and a semicolon for the covariant derivative. And another possibility, which is can also be found in some books, is that you use a single stroke for a partial derivative and a double stroke for a covariant derivative. So these are notations which you should have heard about because you find them in books, but which I will not use. I will use only these symbols, the partial d or the del, nothing else. Oops. Okay, so some other authors write what? They write instead of d mu x, I had d nu x tau, let's stick with this. D nu x tau, they would write x tau and then comma nu. Yeah? So that's just an alternative notation for this. And people who do this, who use a comma for the partial derivative, they use a semicolon for the covariant derivative. So what I denote in this way, they would write in this way. I will never use this notation for the simple reason that my handwriting is so bad that in particular when we have Latin indices, I will never be able to distinguish my commas and semicolons from i's and j's. Yeah, that's the reason why I never use this notation in handwritten notes. But of course, in printed books, you could use it. There should be possible to distinguish the things. Or another alternative is that some authors use a single stroke for the partial derivative. So they write it in this way. Yeah, so that's an index. And in front of the index, there's a single stroke. And people who do this, they would denote the covariant derivative with a double stroke. So that these are notations which you find in books. So I should have mentioned it. So that's how vector fields are differentiated, covariantly differentiated in terms of coordinates. Yeah? What I had mentioned was that if you just consider the partial derivative alone, and what we will discuss in the next worksheet, if you use just the partial derivative alone, these coefficients do not transform like the components of a tensor field. That's the reason why you need an additional structure which gives you these nice Christoffel symbols. And if you add these terms, then the whole thing does transform like components of a tensor. So that's the idea, if you think in coordinates, of introducing a covariant derivative. You need something with the right transformation behavior under coordinate changes. So this was a covariant derivative of vector fields. So now we do it for covector fields. I will again show you the calculation in detail for the covector fields, but then for the higher order tensor fields, I will just write down the results because this would be really probably a little bit boring to do this also in full detail. So now consider a covector field alpha. So this would be something like alpha mu dx mu. So this would be something like that. And I do the quite analogous calculation. I apply the covariant derivative operator in the direction of the basis vector field, or in this term, I have covectors, so I will then write them as a linear combination of the covector basis. So I write down the expression del partial nu, and now applied to the alpha. So what is this? So this is del partial nu applied to alpha mu dx mu. And again, I can use the product rule. That's a scalar field, that's a covector field, and this operator satisfies the product rule. So I can apply it with the help of the product rule. So I have del partial nu alpha mu in brackets dx mu plus alpha mu partial d nu dx mu. Okay? So this here again is a covariant derivative acting on a scalar field. So this is just the ordinary derivative acting on the scalar field. U alpha mu dx mu. Just for clarity, let me make a bracket here. And what is this here? Well, I've just calculated it. I knew what I needed, so that's the reason why I've just calculated this expression. Where is it? It's here. Yeah, that's exactly the expression which we get here. So it comes with a minus. So this is minus alpha mu gamma. How are the indices? The index on the basis vector is the upper index on the gamma. So I have to write a mu here. And then I need this index as the first one here. And I need a summation index, let's say sigma, dx sigma. Yeah? I just inserted the expression for this here, which we had calculated up there. And now again, I just have to rename the indices so I can combine the two terms. So let me rename this mu into a sigma. d nu alpha mu dx sigma minus alpha mu gamma mu sigma dx sigma. And now I can write this with a bracket, taking the dx sigma out of the bracket, and I get d nu alpha mu minus alpha mu. Oh, what is with the indices? What has happened to the mu's? I said I call this sigma. I did it in one place, but I forgot to do it in the other place. Yeah? Of course, I have to rename both indices, so this was an error. So that's the reason why this looks funny, right? You can immediately realize that this doesn't make sense, what I had got here. So now I have d nu alpha sigma, and here I take this out of the bracket, so I have minus alpha mu, that's true, gamma mu sigma, and now it looks fine, dx sigma. So and that, what we have gotten here, that's what one would call the covariant derivative, the coordinate expression of the covariant derivative of a one form. And you see it's formed in a quite similar way as for the vector fields. Up there we have it for the vector fields. Here's this formula. You see again you get an additional term with the gammas, but in this case it comes with a minus sign. Yeah? So when you calculate covariant derivatives on vector fields or on covector fields, you have to be careful. In one case you get a minus sign. So it's not too difficult to learn this by heart. So if you have done this a couple of times, then you will know what's a covariant derivative of a vector field and what a tensor field is. So you just have to keep in mind, in one of the two cases, you get a minus sign. The rest is formed in a very natural way, right? You have these two indices here. These are the lower indices on the gamma. And here you must have a summation. So what else should it be rather than this expression? And again, other authors use alternative notation, so I should write this again. Other authors use this comma or stroke notation. So they would write this here, partial nu alpha sigma. They would write this as alpha sigma comma nu. And they would write del nu, the covariant derivative, alpha sigma as alpha sigma semicolon nu. Or the other faction, which uses a stroke notation, would write this here is alpha sigma stroke nu. Be careful, the order is the other way around, right? So you begin here with the thing which you want to differentiate, and then you write the differentiation after this. Here you apply the differentiation operator, so be careful that the order of the indices is the other way around. And here I have the notation with a double stroke. So this would be written as alpha sigma double stroke nu. Okay, and now we can do this for a tensor field of arbitrary rank. So what would this be? It would have R upper indices, say mu1 to mu r, and it would have S lower indices, say nu1 to nu s. So that would be tensor field TRS of M. And what's the covariant derivative? So I don't show you the details now, I just write the result. Get this analogously. And actually it's not too difficult to memorize this. The idea is, well, we begin with a partial derivative, and then we get correction terms with the gammas. And we need one correction term for each index. And the things come with a plus sign for the contravariant indices, for the upper indices, and they come with a minus sign for the lower indices. That's the rule. And now let's see if I can translate this, what I've said. So if I want to calculate the covariant derivative, say in the, let's write row here, I apply this to A. So I want to say what this is mu r, mu1 to nu s. Yeah, that's a covariant derivative in index notation. So that's a generalization of this expression here for tensors of arbitrary rank. So what would this be? We begin with a partial derivative. A mu1 to mu r, mu1 to nu s. And then I need for each upper index a correction term with a plus gamma. So I begin with a plus gamma. So for the first index, I have a mu1, and this is applied to A, and now I introduce a summation index here, sigma. Let me see. The derivative is the second or the first? That's another thing which you have to keep in mind. Let me just check. The derivative is a first, yes, it's a natural way. So the operator in which I take the derivative is the first index here, and the summation index is the second. So now on the A, we have the first index replaced by a summation index, and the remaining ones would be mu2 to mu r, mu1 to nu s. And I have to do this for each upper index. So the last one would be the one with a mu r, rho sigma A mu1, mu r minus 1 rho sigma, and here I have mu1 to nu s. So now I've done with all upper indices, and now come the lower indices, and the lower indices come with minus signs. So I have gamma, and now I replace the lower indices. So let's replace the first one with a summation index, and I have sigma nu2 to nu s. And the nu2 is obviously needed here. The derivative goes in the direction of rho. And wait a minute. Sorry, that's not nu2, that's a sigma, of course. The summation is over sigma. And the nu1, which I've replaced here, comes here. And again, I have to do this for each lower index. So the last one would be the one where I replace a nu s. So I have here nu s minus 1, and then sigma. The sigma comes here. The rho is the first index on the gamma, and the index I replace is the second index, US. So that's it. So that's the way in which you calculate covariant derivatives of tensor fields of arbitrary rank. Yeah? So for each upper index, you get a gamma term with a plus sign. For each lower index, a gamma term with a minus sign. And then you just have to arrange the indices appropriately. The first index, the first lower index on the gamma, is always the index with respect to which the derivative is done. Yeah? Maybe you should begin with this one. So if you write this, you first write the rho on each gammas in the first place. And then you write the index which is replaced on the gamma in the correct position. The upper indices here, the lower indices here, and the rest must be a summation index. So then you get it. So you can, with a little bit of thinking, you can always reconstruct this fairly easily. Okay, so that's the way in which you calculate covariant derivatives in coordinates, if you have to do it. And sometimes one has to do it, actually, fairly frequently. So these things, I said this already, these things transform like the components of a tensor. They have a tensorial transformation behavior. Here for covector fields, here for arbitrary rank tensors. So these things, this del rho a mu1 to mu r, mu1 to mu s, have indeed the correct transformation behaviors. Of tensor fields. Yeah, this means each upper index transforms with the Jacobi matrix, and each lower index transforms with the inverse Jacobi matrix. And you can check this. Actually, it's not necessary to check this because we have introduced the operator in a way that we know that the outcome is a tensor field. Yeah, so it's clear that it must be this way. But just as a consistency check, you could really verify that this is true. You could write down the transformation behavior for this expression and see if it coincides with the correct tensorial transformation behavior. So I write here, this is clear from how we introduced the del operator. Yeah, it follows from the properties of the del operator, which we included in the definition. As a check, it could be verified directly. Actually, I'm too lazy to do this because it's a somewhat boring calculation, but it's not difficult. And what you would need is the first thing which you would have to derive if you would like to verify this is you would need the transformation behavior of the gammas. And actually that's something we do in the next worksheet also. So we will see how these gammas transform. They do not transform tensorially. Yeah? And that's the fact that the del is not a tensor field, which I've mentioned already. So these objects do not transform just with the Jacobi matrix or with the inverse Jacobi matrix. They transform in a more complicated way, and that will be worked out with the transformation behavior. So I write here non-tensorial. Yeah? Transformation behavior of the Christoffel symbols of the gamma, mu, tau, and that's something we do in the worksheet. Yeah, so you could do this just as a consistency check, see how these things transform. There's supposed to be a nu here, hardly readable. So, and then calculate the transformation of these terms here, and you find that they do transform like tensor components. So again, I emphasize that the partial derivatives do not transform like tensor components. Yeah? But that's fairly obvious, by the way, because for this thing, which is under the derivative, every index transforms with the Jacobi matrix. So if the whole thing would also transform with the Jacobi matrix, this would mean that the Jacobi matrix would be constant. Yeah, that this operator wouldn't act on it, but it does act on it because the Jacobi matrix does depend on x. And that's the reason why you do not get the tensorial transformation behavior. So it's fairly obvious. You just have to look at the expression, then you see that this is not a tensor field. This does not give the components of a tensor field. But with the gamma terms, it does. Okay, so we will practice this in the next worksheet in some detail. So with the help of the covariant derivative, we can now something define which is very important in relativity, that's a parallel transport. So the covariant derivative allows us to parallelly transport vector fields, and if you like, also higher rank tensor fields along curves. I'll draw a little picture. I'll explain it in terms of a picture first, and then I'll write down the equations. So on a bare manifold, without additional structure, there's no possibility to say that a vector at one point is parallel to a vector at another point. We cannot compare different tangent spaces. And such an operator, del, allows us to do this, and that's the background of this name connection. Yeah, where some people call this a linear connection. Connection means that the tangent spaces at different points now become connected, namely in terms of parallel transport. That's what this name linear connection refers to. And then we will see that it also allows us to speak on torsion and curvature. So these again are quantities which refer to a covariant derivative or to a linear connection, what is the same. So parallel transport is our subject now. So I want to explain what it means that a vector is parallel along a curve. So let me draw a picture first. So I have a curve here. What's a curve? A curve is that's a map from a real interval. Yeah, let's say from the whole real line. Could also be a subinterval. Need not be the whole real line, but that's not important. So that's what we would call a curve. Yeah? A map which assigns to each parameter value a point in the manifold. So that's what I've drawn here. So here is gamma s. And if s proceeds, then the point moves along this curve. And in order to bring this operator del into the game, I will assume that my curve is the integral curve of a vector field. So I will assume that I have a vector field, x, such that along the curve, the x is a tangent field. So I will assume that I have a vector field x. If I evaluate this along the curve, so I denote it in this way, yeah, for each s, I get a vector x at the point gamma of s, that this is a tangent field, which we had introduced, I think, in the penultimate lecture. So this was a derivative operator. This was defined as a derivative operator associated with a curve. It just differentiates with respect to the parameter along the curve. We had defined this precisely. And we say that y is parallel along gamma. Y is another vector field. Yeah, if what happens? If the covariant derivative of y in the direction of, x gives 0 along the curve. So if I evaluate this along the curve, then I should get 0. So y is something like this. So I have my y here. So at this point, I have y of gamma of s. And I say that the y is parallel along this curve if this equation holds. If del x, y is 0 along the curve. So this gives me a law of parallel transport. Well, that gives me for the coefficients of the y a system of first-order differential equations, which can be solved with an initial condition. So if you give me the y at one point along the curve, then this condition tells me how it behaves along the curve. So that's what we call parallel transport. So by this equation, we define how a vector field is parallelly transported along a curve. So, which is conveniently, for convenience, written as the tangent field as the integral curve of a vector field x. Yeah, if this equation holds, we say, well, either we say that that x is a tangent field to gamma, or we say that gamma is an integral curve of x. Yeah, that's the same thing. So if the tangent field to gamma coincides with the vector field x, then we say gamma is an integral curve of x. I think this word explains itself. So that's how parallel transport is defined. It's defined along a curve. Of course, we would expect that if we transport a vector from one point into another point along two different curves, then we would expect them to give a different result. So the parallel transport in general will be path dependent. Yeah? So the outcome will depend on the way in which I go from the one point to the other. So there's nothing like a comparison at a distance between two tangent spaces. So I cannot say this vector is parallel to this vector in a general sense without saying in which way I go from one point to the other. So it's a path-dependent notion in general. But we can discuss a special situation that it is not path-dependent. That's quite an interesting thing. But first I will write it in local coordinates. In local coordinates, we have, of course, what? In local coordinates, so I have to write this expression here in local coordinates, del xy. So I would write this as by expanding both vector fields in terms of basis vectors. So that's x mu d mu, and say y nu d nu. Just to be on the safe side, let's put brackets here. Well, in this slot, the thing is linear, so I can just take the x mu out of the slot. So x mu y nu d nu. Okay? But in the other slot, I have the product rule. Yeah? So in this slot, it is not linear. So here I have to use the product rule. So this would be x mu y nu del partial mu d nu. And well, this bracket is actually not necessary, but anyway. And then I leave the basis vector constant, so I apply the operator only to the y nu, and I have the d nu here. Okay. And now you see again the gammas come into the game, the Christoffel symbols, right? So I have here x mu, y nu, Christoffel tau, mu nu, d tau. And here I have x mu. This operator acts on a scalar function, so it's just the ordinary derivative, d nu. Okay. So again, I should change the name of one index. Let's rename the nu into a tau. X mu, y nu, gamma tau, mu nu, d tau. X mu, d mu, y nu. No, this I wanted to call tau. And now I could put a tau out of the bracket. X mu gamma tau mu nu plus x mu d mu, that's a y, sorry, y tau d tau. And now we see what parallel transport means. Parallel transport means that there is a zero along the curve. So now you see it gives indeed a differential equation for the coefficients y tau, right? It's a first order differential equation for the y taus. So parallel transport requires what? It requires that this bracket is 0. So it means d mu partial mu y tau plus x mu y nu gamma tau mu nu is null, is 0. That's the first order differential equation. But actually it's an ordinary differential equation because only in the direction of one vector the derivative acts, right? You have partial derivatives, but only combinations in the direction tangent to the curve occur. So that's actually an ordinary differential equation, although it looks like a partial one. So that's an equation which has to hold. And now we can see what's the condition for the parallel transport to be path independent. Namely, let's consider the special case that all gammas are 0. Yeah? Let's assume we have found a local chart so that on the whole domain of the chart the gammas are 0. Then we see parallel transport requires that the y taus must be constant in the direction of x. So if the y taus are constant, if I have a vector field for which the y taus are constant, then they are parallel along every curve. Then they are parallel in an absolute sense. If the gammas are 0, if this term is not there. So in this case, we can easily characterize the set of vector fields which are parallel. Namely, these are the vector fields for which the y taus are constant. And they are parallel for any curve. So in this case, the parallel transport is not path dependent. So if the gammas are 0, if we can find a chart such that the gammas are 0, then we have what is called a teleparallelism. Yeah? Fernparallelismus in German. So we have the comparison of parallelity in an absolute sense over a distance without referring to a particular curve. But if the gammas are not 0, that's not true. So we observe, let me write it down. So if we can find a chart, and I say already now, in general we will not be able to find such a chart. Such a chart in general doesn't exist. It exists only for very special connections. So if we can find a chart with gamma tau mu nu equals 0 on the whole domain, I denoted that always U. That's the domain where a chart is defined. That's supposed to be an N. If we can find a chart, then vector fields with y tau equal constant, sorry. So the derivative is 0. Y tau equal constants are parallel, are absolutely parallel. That's also a word of putting it. Absolutely parallel. And this means parallel along any curve. So then we speak of a teleparallelism. So we can say the condition of the gammas being 0, or the possibility to make the gammas equal to 0. This is a criterion for having a teleparallelism, for having parallelity without referring to particular paths. So the process of parallel transport is path independent. if we can find a chart in which the gammas are 0. If we cannot find such a chart, and in general we cannot, then we do not have a teleparallelism, and the outcome of parallel transport depends on the way in which we go from one point to another. And that's one way in which one can introduce curvature, which we will do in 5 minutes or so. And curvature will be a measure for the path dependence of the parallel transport. So in this case, where we have a teleparallelism, the curvature is 0. This is another way of putting this. But what we observe from this equation immediately is that if the gammas are 0, then we have an absolute parallelism, a teleparallelism. So let's keep this in mind. I come back to this in a minute. I think that's the right place for introducing another important notation. When we talk about something being parallel, then it's the right place to introduce the notion of a geodesic. This notion will accompany us during the whole rest of the course. Geodesics play a very crucial role in general relativity. So I introduce them here in this place. I just give the definitions and I leave them for a while. And we will come back to this notion later when we have introduced the metric. And then it will be discussed in great detail. So at the moment, I just give you the definition, and then I leave it again, just to come back to it later. But I think that's the right place to introduce it, because it's directly associated with the notion of something being parallel. Namely, having defined parallel transport, we can ask on what condition the tangent field to a curve itself is parallel. So we can now investigate any vector field along a curve. We can ask if it is parallel. In particular, we can ask this question for the tangent field. And if this is true, if the tangent field is parallel along the given curve, then we call the curve a geodesic. So these geodesics are curves where the tangent field is, in a sense, parallel to itself. And that's why some people use, instead of the word geodesics, the word autoparallel. So the notion of a geodesic, as it is associated with a connection, is the same as saying that the curve is autoparallel, that the tangent field is parallel to itself along the curve. So I will write down this definition, and then I will leave it for a while, but I will come back to it later, and we will discuss it then in quite some detail. So the definition is the following. The curve gamma is called a geodesic. Also English or American people do not agree about the pronunciation. I think 50% of them say geodesic and 50% of them say geodesic. So I've decided to say geodesic, but that's just a matter of taste. It's called a geodesic. So that's the first possibility for the name, or what is the same. You can say that it is an autoparallel, maybe written with a hyphen. If gamma dot is parallel along gamma. So we have this here for the special case that not only the x is gamma dot, but also the y has a gamma dot, coincides with gamma dot along the curve. And if this holds, then we say we have a geodesic. So that's something where the tangent field at one point results from the tangent field at another point just by parallel transport. So here the foot point is a gamma of S, and the arrow is a gamma dot of S. So that's how geodesics can be defined with the help of a connection. Of course, this refers to a connection. Yeah? So what I define is not something which makes sense on a bare manifold. It refers to a connection because the parallel transport is defined with the help of a connection. So the notion of a geodesic makes sense only if I have a connection, if I refer to a connection. Okay, so but let me leave this notion immediately after introducing it, just for coming back to it later. and then introduce two other important notions which we will discuss now in some detail for the remaining 10 minutes and then again next week. So for any covariant derivative, we define torsion and curvature. We define, the first thing is the torsion. I introduce these definitions just formally, and I will discuss later where the names come from and what's the geometric idea. But the introduction is just formal. The torsion is defined in this way. The torsion has two slots, and into the slots we put vector fields, and the result is del xy minus del yx minus the commutator of x and y. Remember, x and y are derivative operators, so I can form the commutator. We have discussed this already in the last worksheet. Yeah, in the tutorial the day before yesterday, you talked about this notion. Yeah, it's just the commutator of the two operators. Some people also call it the Lie bracket. That's just a different name, named after the Norwegian mathematician Sophus Lie. Yeah, so that's the commutator. You know it from quantum mechanics. Yeah, quantum mechanics, when you have operators, and it's quite common that you consider the commutator of them. The same thing we do here. These are derivative operators. So we can write the x after y minus y after x, and that's the definition of the commutator. And that's again a vector field. That's what you have shown in the worksheet, which is non-trivial. Yeah? Because if you just apply one operator after the other, so just x times y alone, this is not a vector field. You've also shown this in the worksheet. But the commutator, the antisymmetric sum of the two terms, this does give a vector field again. So that's a vector field, that's a vector field, that's a vector field. So this is for xy of TO1M. So T is an operator which goes in this sense. Yeah? It has two slots. You feed vector fields into the slots, and the outcome is again a vector field. That's again a vector field. Each term is a vector field. So that's the torsion. We will discuss it in a minute. And the other, even more important quantity is the curvature. The curvature has three slots, x, y, and z. It's defined in the following way. It's del x, del y applied to z. That's a vector field, right? That's a vector field. Covariant derivative of a vector field is again a vector field. And then I anti-commute. I commute x and y. Del y, del xz, and I subtract the covariant derivative in the direction of the Lie bracket. So this is again defined for x, y, z in T10 in M. So R is a map from T1OM cross T1OM cross T1OM into T1OM. And now my claim is these two things are tensor fields. So my claim is they are linear over functions in each slot. Yeah? Remember, the del operator was a map of exactly the same form. It had the same domain of definitions and the same image set. But it was not a tensor field. And the reason was that it was not tensorial. There's an n missing. It was not tensorial in the second slot. This year, I will show, yes, I think I can manage to do this today. I will show that this is a tensor field, so that this is tensorial in both entries, and also for the curvature. So this is my claim. My claim is T and R are tensor fields. which means in particular that if T or R vanishes in one chart, then it vanishes in any chart. So, and what's the rank? Well, the rank of T, well, it has two slots. I feed vector fields into it. But the outcome is not a scalar field. So it is not a vector field in TO2. The outcome is again a vector field, which I can view as a map which acts on covector fields. So I have one entrance here. So it is, yeah, because the outcome, the result of applying the map is again a vector field. It's not a scalar field. So I can view this still as a map with one slot. And in this slot, I would have the field covector fields. Remember, the bidual is the same as the original vector field. Yeah? So I can write the tangent space, the space of vectors, as a dual of the space of covector space. So it has slots where covector fields are filled in. So if it is a tensor field, then it is a tensor field of this rank. And for R, well, R has 3 slots for vector fields. And again, the result is a vector field. So it's a co-vector field. So I have a 1 here. So that's my claim. I see I have only 4 minutes. I think I do not do the proof today. I think I do the proof next time. And then we will discuss the geometric meaning of torsion and curvature. So this will be the end of this section on, this will take maybe, I don't know, 15 minutes or so. And the last mathematical structure we need is a metric tensor. So next Friday we will then introduce a metric tensor. And at the end of next week, I think we will have the full mathematical apparatus so that we can come back to physics again. And then we will talk about Einstein's field equation. And after that, about the Schwarzschild solution. So that's the program for the next week. Okay, have a nice weekend.